Hello and welcome back to Basic Topology, the video series where we talk about open sets, compact sets, Hausdorff spaces and related stuff. And in today's part 9 we will define what it means to have a continuous function between two topological spaces. However, as always, before we go into the details, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please use the link in the description to download additional material for all the videos. For example, you find quizzes, PDF versions and books. And then without further ado, let's immediately start with the definition of continuity as we have it in the standard analysis course. So this means that we just consider a function f that maps the real number line r into itself. And then we would speak of a continuous function if we can pull in limits of sequences. So more precisely, we would just take a convergent sequence which we call xn, and this one should live in the domain on the left hand side. And now, since we assume it's convergent, it has a well-defined limit x. So we have convergence in the domain, this is the assumption, and now this should imply that we also have convergence on the right hand side in the codomain. In other words, the sequence f of xn has to be convergent as well. And indeed, we want to have even more. We want that the limit is also given by f of x. And this is it. This is the definition of continuity by using sequences. And actually what goes in here is that we have a notion of convergence on the domain, but also on the codomain. And roughly speaking, the function f connects these two notions of convergence. In fact, such definition can also be used in a general topological sense, but it's easier to go back to the basics. So you know the starting point of a topology is just given by open sets, and it's better to use them to define continuity. So this will be a really general definition, and it also contains the classical one from above. So what we have here are just two topological spaces and a map between them. So let's say on the left hand side we have the topological space X, and on the right hand side the topological space Y. They can be completely different, but they are connected by a map F. So on the set level we just have F that maps X into Y. However, now the question is, what happens to open sets that we have on the right hand side but also on the left hand side? And exactly there the notion continuity comes in. In fact, we say that a map F is continuous if the pre-images of open sets are still open. This means we fix an open set on the right hand side and then we look at the pre-image of this set under F on the left hand side. And then obviously, in general, this pre-image here does not have to be an open set at all. So it's definitely a real requirement we want to have here, and this is what we call continuous. So let's fix that in a definition here. No matter which open set B on the right hand side we choose, we always get an open pre-image on the left hand side. So this pre-image of B under F also lies in the topology. And an important thing you should remember here is that the topologies on the right and left could be completely different. Okay, so this is the general definition when we have a map between two topological spaces. But now you might already know that we are mostly interested in the case of real-valued functions. Which simply means that the topological space on the right hand side is quite simple because it's just the real number line with the standard topology. Therefore we only have one general topological space X given, and then we look at maps from X into R. And obviously there the same definition of continuity as above can be used. The only thing you have to know is that on the right we have our standard topological space given by the standard topology. However, now the advantage is that the real number line has more structure, so we can talk about different concepts of continuity. And the first one I want to talk about now is that the function is upper semicontinuous. And as the name suggests, this should be a special case of a continuous function. This means that we don't look at all the pre-images of open sets, but just at some special ones. Indeed, we take the interval from -infinity to a given real number lambda. And now this pre-image should be open in the topological space X, no matter which lambda in R we choose. And please note here, this collection of intervals is not enough to cover all possible open sets in R. And maybe a good way to remember this property of semi-continuity is to look at the graph of a function. So for example, you could imagine that we have such a graph where the function makes a jump at this point. And now we are allowed to fix any lambda on the y-axis. And now what we do is we go from minus infinity to this lambda, which makes sense because in R we have an order. This does not work on the x-axis because in our general topological space we don't have an order in general. This is the reason why the term upper semicontinuous only makes sense when we have the codomain given as R. And now finally in this picture here, we want to visualize the pre-image from the interval from minus infinity to lambda. So we just have to find the points that are mapped to the interval, and this is not so complicated as you can see here. And now the function can only be upper semicontinuous if this pre-image is an open set in our topological space X. And in fact here, if X were given as the real number line with the standard topology again, then we would have open intervals and then the union is also open. However, you also see this only works because this jump point here is set at the upper point. And you can remember this as the reason why this one is called upper semicontinuous. Hence it might not surprise you that we also have a term that we call lower semicontinuous. And obviously there, the jump point from before has to be on the lower level. And more concretely in the formula, now we would look at the pre-image of the interval from lambda to plus infinity. And as before, we want that this pre-image is open no matter which lambda in R we choose. And actually we can completely copy the picture, the only difference is now that we consider the interval from lambda to plus infinity. And most importantly, to get a lower semi-continuous map, we have to fill in the lower point in the jump point. Because then it's totally clear that we get open intervals again if X is given by the real number line again. Therefore, this is a typical picture of a lower semi-continuous function. Okay, so now we have the two notions of semi-continuity, and indeed both things together just gives us continuity from before. And in order to close the topic, let's look at an important example. This one will be a so-called indicator function, or also called characteristic function, of an open set of a topological space X. So let's call this open set simply A. And in fact, the common notation for the indicator function is to use a lowercase chi with index A. And the definition is quite simple. We only have two values, 0 and 1. And there I can tell you the value is chosen as 1 if and only if X lies in A. Therefore, if X does not lie in A, we set the value to 0. And now, because we only have two values here involved, the graph of the function is also easy to visualize. Perhaps we just consider the case that A consists of 3 parts, and then A looks like this on our x-axis. And then if we have the value 1 here, we also find the lines of the graph there. And obviously all the other points are just sent to 0. And now since A is open, we should assume that the jump points are on the lower level. Of course, this is just our visualization here, because we actually have to show that our characteristic function chi A is lower semi-continuous. So by definition, we have to look at the pre-images like before. And since the function only has two values involved, this is actually quite easy. So for the first case here, we could take lambda greater or equal than 1. Then no point at all is sent to this interval, so the pre-image has to be empty. And now most importantly, the empty set is definitely an open set. So for all these lambda values, our condition is satisfied. And then in the next case, let's take a lambda between 0 and 1. So lambda definitely has to be smaller than 1, but it can be equal to 0. Hence, no matter which lambda we have, the only value that lies in this interval is actually 1. And by definition, the preimage of 1 is just our set A. And also there, most importantly, A is an open set. And then finally, we can consider all lambda values that are negative, so lambda is strictly less than 0. Therefore, our interval here definitely covers all the values we have, so the preimage is the whole set X. So indeed, all points from X are sent to this interval in that case. And by definition of the topology, X is an open set as well. So the conclusion is clear, such an indicator function for an open set is always lower semi-continuous. And I can tell you this is an important result because such indicator functions play a crucial role in measure theory. And indeed, soon you will see that facts about lower semi-continuous functions and upper semi-continuous functions can be used in technical proofs about continuous functions. So you can already see, in the end, the important set of functions will always be the full continuous functions. And why this is the case, I will tell you in the next videos. So I really hope I meet you there again, and have a nice day. Bye bye.